तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We were looking at one of the design applications for say the traffic light controller, and for which we have seen design as well as the waveform for analysis, and we found that waveform conforms to the design we have actually made, and we will now see the test bench for the same, and test bench goes something like this, and this is the title for the traffic light controller test bench. And as usual we have a define statement which defines the clock. For 50 megahertz we put 10 in this variable here, and that being the half time period, and we include the actual design traffic controller here by the statement include. This is the design file, and this is the module we declare here, and this is the traffic controller test bench, and this is the module which is the current file. And herein we declare all the inputs as reg, namely clock, reset underscore n, then blink. This is to blink the yellow lights beyond the traffic hours, and we need to instantiate the traffic controller design module. That is being done here, and the only instantiation is this TC1, this similar to U1 U2 in the chip that you really design on a board. And you need to declare ports by name, and these are all the inputs we have already seen, and these are all the output lamps, 16 in number here, starting with the main green, side red, and so on, Y for yellow. And we also have a right turn for both main as well as side, and they are all basically green lights, and we have a blink control. And beyond traffic normal traffic hours we switch on this control, either it is done manually or automatically by using a timer, which can also be designed into this very traffic controller design that we had done before. And we start the initial block right here in order that we may initialize all the input signals, namely clock, reset n and blink, to all of them 0 except for the reset n, because this is active low. And we pulse this reset here, and for 20 nanoseconds, and once again we restore back, so that normal operation starts right here, and we allow enough time for it to go through at least one full sequence. I think some 8 sequences were there, which we have already seen earlier right on a PowerPoint presentation, and it may be one sequence or more, and for which we need at least this much nanoseconds, and beyond which we will activate the blink in order to check whether all lights are blinking. In fact, we have seen the waveform and confirmed earlier, and that it is really working. And once this is done, after a while we will switch off blink, so as to resume the normal traffic light operation. And after some gap, it need not be such a huge value here, it can be even just 40 nanoseconds, and then we stop here. And this test bench for this is a very simple and straightforward thing which we have already seen, and we run the clock by this statement, and this is program for 10 right at the beginning of the code, and this is to toggle the variable called clock, and every 10 nanoseconds it will toggle. That means 20 nanoseconds will be time period, and hence 50 megahertz which we have already listed earlier. And this completes the test bench, and before we wind up we have as usual assignment for you, and I will read the assignment and explain what it is. The design covered does not have pedestrian crossing, and include the same and redesign. You may include push button requests for the same, restricting only the free left traffic whenever a pedestrian crossing request is made. What we had earlier was the main flow as well as side flow straight traffic would imply that pedestrians can cross at the other road. For example, if it is a straight main and on the side road there is no traffic, therefore it can cross, and pedestrian can cross here. And even here the complexity is that we have a free left traffic, that will be a hindrance for the pedestrian. So what we do is we will provide one more push button switch for each of the 4 corners, and then allow the pedestrian to cross based upon that, and in which case whenever a pedestrian crossing push button is pressed, that corresponding traffic free left will be suspended for the time being, and for the duration of the programmed time, and you have to add that in this assignment, and that is what this is. And the second assignment is we have been doing for places like India, say Asia, and closer countries, and that is left flowing traffic. On the other hand, in USA and European countries it is right flowing traffic. So redesign the whole thing that we have done, including the adding pedestrian crossing, and cater it for right flowing traffic. This is the second assignment. So now what we are going to see is we are going to into the design of DCT-Q, and an image such as this we are going to process, and before that let us have an introduction to image and video compression, and so I will go through some of these points first and then explain later on. So image compression finds wide use in applications such as education, industries, medicine, defense, training, entertainment, sports, multimedia, desktop publishing, video telephone, video conferencing, digital cameras, and so on and so forth. There is an innumerable scope for applications, especially in image as well as video. The differentiation between image and video is image always refers to a still picture, whereas a video is a series of such pictures, one different from the other one only by slight amount, and depending upon the actual motion involved in the video picture. And as such, for raw video, let us say for 2 hours of color motion picture of very high resolution, say 1024 into 768 pixels, you need a very high storage of the order of 396 gigabytes, and also we need bandwidth requirements much higher. For example, you will be ultimately after the point here is we need to compress, and after the compression we need to transmit over the serial channel, and if you are to transmit this same thing without compression, say that is namely the raw signal, you require a very high speed channel for that. So speed required for real time transmission of a video sequence of this size, that is this size, at 30 frames per second. This 30 frames per second holds good in USA and other regions, whereas in India and other places it will be 25 frames per second. If you are to transmit this over a serial channel, it requires a stupendous bandwidth, say 540 megabits per second, and so this will restrict, put together with this high storage, this will be a big constraint, and hence the need for compression here. the compression is so to say an inevitable thing, and in order that we may contain the storage and transmission in manageable limits. So this is a hot field even as on today, and it has led to a number of developments among researchers all over the globe for various image compression techniques, say development of new algorithms as well as implementation as VLSI, and all these methods aim at image compression and aim at reduction in the amount of data without appreciable loss in the image quality. So we need to achieve as much compression as possible, and so that we can limit the storage as well as bandwidth requirements, and but at the same time we should not sacrifice too much of image quality. In fact, any compression would involve sacrificing quality. The question is how much we can sacrifice, and that is what it is. And these designs will have to conform to standards, otherwise there is no communication between one design and the other, and that is what is also important is the connectivity and compatibility among different services, for example video phone to video conference or to MPEG 2 and so on. We will see a little more in detail next here. So design must conform to standards so that systems developed by different industries worldwide can communicate with one another. Connectivity and compatibility among different services, video phone, video for conference, MPEG 1, MPEG 2 are as well important. So all these standards we have named deal with only the basic services, providing lots of room for innovation in the form of developing new algorithms or the type of implementation, whether it is an FPGA implementation or ASIC or any other implementation, and it does not cripple your innovation or entrepreneurship. And several such standards are available, and we will look into some of these standards, basic features of this. For example, JPEG stands for Joint Photographic Experts Group, and this is basically based on what is called Discrete Cosine Transform, abbreviated as DCT, and this is based on a transform. Transform in sense an image is taken and transformed to a frequency domain, and that is what it implies here. So also JPEG 2000, in JPEG 2000 instead of DCT a DWT is used. DWT stands for Discrete Wavelet Transform. So the reason this is of a recent origin, and both are for processing still images. So in JPEG you have if you compress too much, you have what are known as blocking artifacts, and in JPEG 2000 these blocking artifacts do not manifest, and in a way regarding quality JPEG 2000 is better than JPEG, and but you have to pay a price for it. This is very computationally intensive when compared to the DCT, and therefore you can't achieve real time speeds for high resolution pictures of the order that we have already seen before, which can be in this design that we are going to present. We will see that very high quality, much greater than the picture size that we have mentioned before, can be achieved by using JPEG or for that matter MPEG 1 and 2, and MPEG stands for the motion picture, and this is another standard 1, 2 and 4, 7 are all there. For multimedia that 4, 7 etc. can be used, and you have in one more for multimedia, it is called MHEG, and there is also a HD TV, this is a high density TV. For all these basically they are all motion pictures. It's a, I'm sorry, it's a high definition TV, and you also have one more standard called for video phone and video conferencing, that is H261, and earlier version was 263. I think this is the better than 263, I suppose. So this covers quite a lot of range, right from still picture to motion picture, and video phone, video conferencing to broadcast quality video, which we will be listing here. So this function modules used in these standards, for example a JPEG is we are not going to cover JPEG 2000 because that is DWT based. So we are going to concentrate on DCT based, and all these standards listed are basically the same DCT is going to be used, and this is for still picture compression, and the modules that we will be using and designing will be the DCT, then quantization, next is what is called Huffman coding, and it also goes by the name VLC, which is abbreviation for variable length coding, and naturally this will be at the encoder stage, wherein you take a raw image and compress by using these techniques and then send it over a channel, and at the receiving end, which is called the decoder, and we had to do inverse operations of this. For example, VLD will have to be applied here first, followed by inverse quantization and followed by inverse DCT, and for these are all motion picture. For video conferencing, the total transmitted bit rate is rather low, and depending upon p value you can have right up to 30 into 64 kbps only you can go. So, this kilobits per second. So, because this is a serial transmission, and we also have MPEG 1 for digital storage, say namely on the tape and any other storage media, and it can go right up to 1.5 million bits per second, and for MPEG 2 it gives a broadcasting quality even for TV you can use, and transmission rate is quite high, 15 Mbps, and so here what is said is DCT, quantization, Huffman coding and their inverses, as well as what is called rate control. Rate control is part of the VLC or VLD, in the sense that suppose depending upon the picture you may be compressing, and we can't predict how much will be the utility as far as the transmission channel is concerned. It may not be utilized for brief while. So, if you look at the bit stream coming out, it will not be uniform. So, in order to make it constant and uniform, you need to place what is called rate control, which is part of this VLC, and we are not going to discuss VLC. What we are going to do is only DCTQ to start with, and IQ IDCT has also been done, but we are going to use only the end result because it is so design is quite involved, and we will have to restrict it, and even this goes to some 124,000 gates or so DCTQ alone, and so then comes what is called motion estimation and motion compensation. A new algorithm also has been developed by the speaker, just as for DCTQ a parallel novel algorithm has been developed, and which we will be presenting a little later, and but we will not be covering this motion estimation, this beyond the scope of the present lecture series, and all these things are involved in motion picture. For example, 261 for video telephone conferencing, then for storage as well as for broadcast quality compression, and for all this DCTQ, IQ IDCT are common to these standards, and that is the reason why I had taken DCTQ to start with, and this also will be used, although it will not be explained, and it is it will not be explained also because it is exact counterpart of DCTQ. It employs the very same algorithm used for DCTQ, and in all these the basic operations that bring about compression are this. For example, discrete cosine transform, this prepares the ground for the compression, it does not bring about the compression all by itself, it prepares only the ground for that. So, in the sense what we do is we apply a block of image and transform it to frequency coefficients. Out comes some 64 coefficients if you process a block of size 64 pixels, and so these things, I mean these coefficients pack varying energy of the image in different coefficients. For example, the very first coefficient stores 8 times the average of the image information, and rest of the coefficients, say namely 63 coefficients, store only balance, and this is followed by quantization. In quantization what we do is we make an attempt to make this DCT coefficient 0, as many coefficients as possible, and make it 0. The purpose of making it 0 is we do not have to code this quantized value, and if you, that means to say this coding is done in the Huffman coding or variable length coding, abbreviated as VLC, and what this code does is it frequently occurring intensity value of any signal, which will get reflected as a discrete coefficient DCTQ coefficient value, and that is taken as the input. That DCTQ output is parallel, say for example it may be a 9-bit, and that will be the input for the variable length coding, and out comes just single bit, and it is a bit stream, and this bit stream is a compressed stream, and when compared to the original input, you will have a factor of 10 to 50 compression depending upon the algorithm we adopt and the techniques we adopt. The architecture also plays a great role in that, and the purpose of applying this variable length coding is to bring about the compression. The compression affected in this stage is even more when compared to the quantization stage, and this is bringing about compression since it succeeds in transforming most of the coefficients to 0, which need not be broadcast and which need not even be coded, and all these we have seen which bring about the compression are common to all the standards mentioned earlier, namely JPEG through MPEG-2, and still image or iframe, I mean any still image that you have is processed block by block, and using that DCTQ, which we will be seeing a video encoder block diagram shortly, and out comes through the VLC bit stream, and before that we can perform even the inverse operation, namely IQ IDCT, and then form a separate frame that is known as iframe, and this is useful for motion picture processing, which we will explain a little later. This iframe employs DCT quantization as well as VLC, and it exploits what is known as spatial redundancy. If you take a picture as we have seen before, namely the parrot, so what you have is a 2-dimensional picture. That means width wise and height wise the 2 dimensions are, and that is nothing other than a space, and whatever redundancy is there in intensity information as far as adjoining pixels are concerned, they are removed. So thereby we bring about the compression. So this DCTQ VLC all put together accomplishes this task of spotting out redundancy in the spatial domain of the picture, and then bringing about the removing the redundancy and retaining only that which is required as far as the information is concerned. And in contrast to this iframe, we have what is known as P frame called predicted frames, or B frames, which is bidirectionally predicted frames in motion pictures. In a motion picture, as you see, if you see, you would have seen filmed rolls, and if you inspect the roll, you will see that there is in between two sequence, adjoining frames, there is only a small motion involved. So what is the need for coding it where there is no motion involved? We can as well retain the same frame, previous frame. So that is the basic idea in this motion picture processing, and it is also the idea in motion estimation algorithm, motion compensation as well, which we have already mentioned. And so wherever there is a motion change, only there we need to code, and coding is obviously application of DCTQ followed by VLC and so on. And the motion picture processing employs motion estimation and compensation in addition to DCTQ and VLC. We also need this DCTQ VLC because if you want to find the motion between two successive frames, you will have to take one block. So it is known as a macro block. It is consisting of 16 by 16 pixels, and search in a window which is 4 times that area, and in the previous frame, so as to look for where the particular block has or macro block has moved with reference to the previous thing. And for this it involves lots of algorithms are in work, and the speaker also has developed a new algorithm, and one of the fastest available, and we will not be covering those, and affecting more compression owing to exploitation of temporal redundancy. So we speak in terms of frames, that is frame to frame, it is differences in the time. So temporal refers to the time. So here in the within the image, whatever redundant information is there, this DCTQ VLC removes that, that is confined to the space, whereas frame to frame we speak in terms of time, that is why it is called temporal redundancy here. And herein we expect much more compression than is possible here, in the sense that we need to code only where there is some motion, and majority of motion, for example you are looking right at the image here, and there is practically no change in motion. So there is no point in coding the same thing again and again frame after frame. So in such cases even if you see the speaker you will see only the lip movements or head movement, eye movements and so on. So what is the need for coding the rest of the picture? So that is precisely the background here, and thereby you achieve much more compression there. So a typical video encoder will be like this, and these are all the signals pertaining to the system bus from or to host. We have what we are going to do is we are going to design IP cores for DCTQ and IQ IDST and so on, right, although we are going to see only the design DCTQ here, and this is the total picture of a video encoder. So this block diagram of a video encoder is shown here, and as explained before, we first take one block of image and then apply DCTQ. Out comes corresponding 64 coefficients here, and if you do the inverse operation you can recreate the very same image that you have put in here, and that is what is called reconstructed image, that can be stored in RAM here, and that is what is designated as previous frame store here. And you need this one because in order to perform motion estimation we need the previous frame, otherwise we cannot see where the how to process the motion actually. So we take a macro block as mentioned earlier in the current frame and look for the shift in the previous frame, and that is what this algorithm does. And finally it will create what is known as motion vector, which will say it has moved by such and such place. The xy coordinate will be transmitter, using which at the receiving end will be easily reconstructing that motion, and there will be no need for sending the previous frame, only we need to send that particular small macro block and where there is a motion change. And regarding this iframe, so we apply block by block, out comes the iframe here which is stored. It is also transmitted after doing VLSI and via first in first out, typically 16 kilobits depth should be enough for FIFO storage, and out goes the bit stream. If rate control is in place here, then you will have a constant bit stream here, and this is the video encoder, and that will be at the receiving end. This will go right out at the channel as serial channel, and unfortunately we can't use the present day networks because you can't process any real time image, and even in still image it will be difficult, and we need a dedicated channel for that. And at the receiving end you receive this bit stream, and there will be FIFO there also, and from that we do inverse operation, say namely VLD, D stands for the decoder, and get a parallel information which is DCTQ equivalent here, and we there will be this element this processor there at the receiving end, and that will be processed, and you will get a recovered signal here, and that signal will be same as this one. Ideally we will be having a look at the images that we get out of running our design using both MATLAB as well as Verilog later on. And so is this clear to you? This is the encoder, its counterpart is in the decoder. So what goes out is highly compressed stream. For example, it may be whatever is the image you compress by a factor of 10 to 50 anywhere, and then only send here. Thereby you reduce the bandwidth requirements as well as storage at the receiving end. So as far as color processing is concerned, we basically have red, green and blue as primary colors for display on the TV monitor that you see, and or on the computer terminal that you have. It is basically a CRT display, and but they are not efficient in terms of transmitting real world pictures, processing real world pictures. It is not that efficient. So, what we do is we need to do first what is known as a gamma correction. The reason for not being efficient is CRT, I mean electron beams form the intensity in a CRT corresponding to the image information that it receives. So, the intensity is proportional, directly proportional to power such as 2.2, say voltage is this signal voltage, V to the power of 2.2 will be the response here, that will be the intensity of the on the CRT. So, naturally this is a non-linear thing. So, in if you use what is called gamma correction, which is same as this here, gamma factor for this signal such as NTSC signals. This NTSC signal is for say American USA, and for PAL, SECOM, for Asian and Russian I suppose, and picture size are also given here. This 720 by 480 pixels here and 720 by 576 here, and they are what are called interleaved, that is in sense in order to avoid flickering they have separated the entire picture into odd and even lines, for that matter frames, and thereby reducing the flickering, and so that is called interleaved. And in CRT monitor etc., what is popular is non-interleaved. So, that means say line after line it is processed all the 720 lines, and in each line 480 pixels and so on. And for NTSC it is 30 frames per second we have to achieve the picture rate, because they are all concerned about motion pictures, and for PAL it is 25 frames per second. So, here we say that we need to incorporate gamma correction. If we are to do at the receiving end, that we have this basically a TV at every home you will have, and there will be two innumerable, and so a better thing in order to save the cost for the consumer will be to take the complexity right at the camera end, and inverse of this I think a factor of 0.45 will come, V to the power of 0.45 will be the intensity which needs to be corrected at the camera end before transmission, that is what is mentioned here. And as far as the standards are concerned, even this gamma corrected RGB is not adequate. So, we and it is not efficient once again, and I will read out this. Since our eyes are less sensitive to color components than luminance component, many standards use luminance and color different signals such as Y, CB and CR. So, Y is known as the luminance portion, and CB and CR is known as the color portion, and do not correlate this one to RGB straight away. Suppose you take CB and say I want a color picture, you may get some outline of picture but not the true color, right. So, also with Y you will not get the monochrome picture. So, it is only the reason is this Y, CB, CR are governed by these expressions here, and which are derived from RGB gamma corrected, and gamma correction is with a prime indicated here. These are all the expression that we need to conform to, and the standards all JPEG through MPEG 2 and even beyond all demand the use of YCB CR format. And another important thing here is I will read out this. CB and CR signals are subsampled with respect to the luminance by 2:1 in both vertical and horizontal directions. I will explain this in a minute, thus affecting more compression as well as higher speed of implementation, and macro block structure for the same is shown here. So, now what we have seen is we have seen a picture, and the entire picture, the picture that you saw right at the beginning, the parrot namely, is actually 1024 by 768 true color. That means you need 3 bytes for representing a color of YCBCR, or if it is even gamma corrected RGB also in the raw format, you need 3 bytes for representing for each byte for each of the color component. And if you do that one, you will be needing in order to process, say this is what is called a macro block. It consists of 4 blocks. It is only for convenience sake we divide it as a macro block, and the standard demands this, and so each one is a block. And what is a block? It's a block is nothing but a collection of 64 pixels arranged as 8 pixel by 8 pixel, and we will be looking at what a pixel is right with respect to the actual image we saw before. and this is what is termed as a block, and 4 such blocks would constitute a macro block, that is what is here, and each of them represents a block here. So suppose you want to transmit a full color, process a full color. So what you need to do is, instead of 4 blocks here and just 1 block shown here for the color component, we actually need another 4 here and another 4 here. That would take total of 12. You have to process 12 blocks. Each block processing takes the same time. So that means to say it when compared to a monochrome, for which we need only 4, for processing true color we need 3 times that. So that means if you want to 3 times the speed, so I mean sorry 3 times the time you require, that means the throughput is just 1/3 of what you get in monochrome. In other words, resolution of the picture will get hit, so you will have to scale it down by a factor of 3. So are you clear about this? If you process more blocks it takes more time, that is what I am trying to say. So in order to contain this one, the trick played by and recommended by the standards is this. We have also already seen that our eyes are sensitive only for luminance and not for the chrominance. A color component, you can easily fool our eyes by taking only alternate pixel color and processing them. So for example, in this block, hoping that you can see independent block, take the first pixel, then the third pixel, then fifth pixel and arrange them. If you take total macro block which will contain 16 by 16 pixels, you will have you will extract only 8 by 8 block. So that is what is shown here. So this corresponds to one component, color component CB, and similarly there is one more component CR, and CB CR are all derived by this expression what we have already seen. Why CB CR? In fact, notice that all the RGB components are embedded in this. So do not seek for a one-to-one correspondence. So are we clear here? So what we have here is, instead of in this particular recommended by the standard, we need to process only 6 instead of 12. That means half the number of blocks only we need to process. That means instead of full color processing, we will have double the speed that can be achieved with this particular recommended thing. It is just 1.5 times the monochrome speed. So now what we will see is, we have developed a novel parallel algorithm for fast implementation of DCTQ, and we need to go into a little theory for a while and follow this carefully. See, DCT is defined by this. See, it is it's not a very complicated affair, and CUs, CV are all constants, but it depends upon the spatial coordinate of the image. So what we do is, we take an image, the image is fxy, xy are the coordinates, and a block of image we have already seen what it is. Suppose you number those block arbitrarily down as a 0 0 coordinate, and like you refer to any Cartesian coordinate. So you can each unit can be marked from 0 through 7, so instead of 1 to 8. So if you do that one, you can cover for this sigma is for all summation, and if you just apply for this alone, so it simply implies summation of all the pixel intensity. So to keep it simple, let us deal only with one component, color component, or just a plain monochrome. And if you are processing color, we are dealing only with one of the components, either Y or CBCR. So this is a cosine transform that we are applying here, and there are two cos terms, and this is because we have a 2-dimensional picture, and we need what is called 2-dimensional DCT for that. Similarly, you also have a 1D DCT, wherein only these two terms will be there, only one sigma will be there, only one constant will be there, and this is basic definition and for DCT, and U is also likewise 0 through 7. That means to say you have a total combination of 64 here. So because 0 through 7 is 8, so 8 into 8, so totally you can have DCT, this is called a DCT coefficient. So you have if you take one block of image which consisting of 8 by 8 pixels, out comes 64 coefficients here, and mind you it has no direct relationship between each of these pixels. You can't say one pixel is related to one coefficient. In fact each of the coefficient is conglomeration of all the pixels information. For example, the very first coefficient is known as DC coefficient, and that is obtained by assigning u v equal to 0. So this will boil down to cos 0 which will be 1 here, and so what you have here is, what is left here is only this. So this is nothing other than take all the pixel intensity for the entire block, that means 64 pixels, add them together, that is what is implied here by this. And if you take for uv it is 0, so what you have here is 1 by root 2 and this contributes to 8 together. In other words, DC coefficient which is uv equal to 0 each, and that is the very first coefficient we are going to compute later on, and that is nothing other than all pixel intensity in a block divided by 8. It is not an average. Many people mistake it as average of all the pixel intensities. That is simply not true. It is actually average is 64 times division, whereas we deal with only 8 here. So it means 8 times the average information is contained in just one coefficient. In other words, if you take just DC coefficient alone and transmit, code it and transmit and receive at the other end and do the inverse operation, you will still recover the whole image. Only details may not be that easy to see, and you need much higher coefficients in order to create the detail, especially the at the sides, be it vertical or horizontal or even through diagonal and so on. So this is the basic DCT transformation, and the CUCV is 1 by root 2 only for u equal to 0. For all other values it is 1 here. So here now we are going into the new algorithm developed, I mean for the sake of implementing it as an ASIC or FPGA, and in general as a VLSI. So basically if you look at this expression here, you can also see that it can be expressed in the form of a matrix. For example, this is 0 through 7, that means only 8 combinations are there. Similarly for if you take, let us say I bifurcate half Cu and then half Cv and assign that one, absorb that in this cost term, half the thing in this here and half Cv in second thing, and you can then represent it as an 8 by 8 matrices. 3 such matrices will be there, and first cost term will get reflected in C, and this will get reflected in another CT, which is nothing other than same matrix but transpose of the same. What you see as a row there will be a column here, that is what you imply by the transpose. So DCT can be conveniently expressed as a matrix here, and where X is the input image, a block of image is what is being referred here, therefore it has got to be 8 by 8 size, and similarly C we have seen because it is varying from XY 0 to 7, and naturally C and CT also will be an 8 by 8 matrices, and this we have already explained in the present implement algorithm. This has been absorbed in C, and the other portion half CV has been absorbed in CT here. This can be expanded here so as to get an understanding here, and there were dots here, unfortunately it got changed, just ignore this. So here the first matrix is C0 C01 and so on up to C0 7. This is a first row. Like this you have 8 rows, and same is the case here, except that this row becomes a column here, and that is how it is, and X stands for the actual image block. So you have each of them correspond to 8 bits, because we are going to process only one color component at a time. We saw that only 8 bits are required, that is 1 byte only is required. So each of this will be an 8 byte information. So if you want to evaluate this DCT, you just see the number of calculations, multiplication involved, it is quite a stupendous value, right. Let us say the purpose of looking into the algorithm and is to make it convenient for FPGA implementation, which can yield a very fast high throughput, high throughput, and that is the purpose of deriving and contributing new algorithm, and which we are going to see presently. So now how do you multiply two matrices? You have three matrices, you have to multiply them. So in order to multiply that, you can do only two matrices at a time. So row of a particular thing is first matrix is taken and multiplied element by element with the column. So that is namely C0 multiplied by X0, then plus C01 into X110 and so on. So that constitutes one particular element which is P00 here. So note that we need 8 multipliers in order to accomplish 8 multiplication, and one adder which we need for adding all the 8 terms together. So it is an 8 input adder. If you would recollect, we have already seen the design for multiplier and adder, and we are going to use precisely the same design and here, and therefore those design will not be repeated here, and while treating the Verilog code. And in this case you multiply this row by column, and in the very first cycle, as far as the implementation is concerned, you need one clock, in one clock cycle we can accomplish. You may wonder how it is done, we will see that presently. And once it is done, we repeat the same thing, retain the same row, but change the column now, second column, and get P01, and so on for 8 clock cycles. You would have got the entire row of this, and we term this as a partial product here. And once this row is complete, we can start multiplying the second one. So we repeat the same multiplication here. So element by element, P0 into C0 plus P01 into C01 and so on. So again you require another 8 multipliers here, and one more adder is required for adding those, and when this is done, you would have got the very first DCT coefficient here. That is what is shown here, right? And now the crux of this algorithm is here. So as you are evaluating this DCT coefficient, in concurrently you can also evaluate this coefficient, because this is quite free to execute this concurrently. Concurrently means simultaneously. So that is the contribution of this algorithm. So thereby you save time, and it is the whole thing can be pipelined in such a fashion, and you will get the output at the rate of one coefficient at every clock pulse. So that is the best possible speed you can conceive of, and because of this regular structure, in fact I mentioned some over 100 technical papers are there in journals as well as international conferences, and all of them are oriented towards reducing redundancy in this, and by using what is known as butterfly structure, and thereby regularity of the structure is lost, whereas here we are retaining the regularity of the structure and playing some other trick so as to get a very high throughput which cannot be achieved in the butterfly structures, and other researchers have done. That is the reason why this algorithm is claimed to be the fastest as on today. And this is the basic DCT, wherein each of these terms is just put here, which we have already explained before. And I will just this completes the DCT. I will just summarize what we have done here. The two-stage matrix multiplication can be implemented by parallel architecture, wherein 8 partial products, which are the row vectors of Cx generated in the first stage, are fed to the second stage. Subsequently 8 DCT coefficients, this is after using the partial product. So corresponding to a row of Cxt, this is the DCT coefficient that emerges, are generated by multiplying row vector of Cx by the Ct matrix. So while computing the I plus 1th partial products of Cx, the ith row DCT coefficients can also be computed simultaneously, since the ith partial products of Cx are already available. This is the basic contribution in this algorithm, which we have explained before. So application of DCT on an 8 by 8 pixel block thus generates 64 coefficients in a raster scan order, which we have explained right at the beginning. So the next step is what is called quantization, and quantization outputs can be obtained by dividing each of the 64 DCT coefficients which came in the previous step by the corresponding quantization table values given in the standards. This is part of the standard, and it is another 8 by 8 matrix with elements of 8, 16, 16, 19, 22 and so on. So, for example, if you take a DCT, if you evaluate the DCT for one block, sample block here, and you get a 1260 DCT here, and if you divide this by 8, which is the quantization matrix table, one of the values, you get 157. This is after rounding off. So, this is what is called a quantized output. So, as I mentioned earlier, DCTQ purpose is to convert as many zeros as possible, which need not be encoded in the VLC, and that is how we bring about compression. And so, we will see more in our next lecture. Thank you.